Yeah, because I would just try to draw it out again and see what you get and see if you
Okay.
get that. But kind of, right, you're thinking of how can I minimize formal charges, so that's where that comes
Uh-huh.
in. So the chlorine doesn't have a formal charge.
Mhm.
And then those two oxygens with the double bonds, their formal charge is minimized, so your only charge is on that one oxygen.
Okay.
But you might be able to draw other structures. That's why I was curious what you got,
Okay.
because then we could determine whether it was like how bad of a structure it was. Because maybe there's something. Let's try. Let's try one permutation. Of chlorine and
So the first 6 fingers.
how many total electrons are there?
There's 26.
1, 2, 3, 4, 5,
So
6, 7, 8,
geometry.
5, 26. So we do that 1, 2, 3, 4, 5, 6. The problem with this is chlorine has a positive formal charge in those two, so that's where you invoke the double bond. But yeah, you have to tell me what you came up with.
I wasn't, I think what my issue was I wasn't thinking about the formal charges. And that's their natural charge before the bonding.
Well, the formal charge is just kind of like our electronic bookkeeping. Because the formula, right, is just our valence electrons minus number of bonds minus electrons. But what that's kind of telling us is like, is it happy in a sense?
Right.
And so that's where it kind of comes from, is just more formal bookkeeping and then trying to like figure out how to distribute the electrons. But yeah, I would just try to redraw it with a fresh blank slate, see what you get,
Yeah.
and then we can talk about it too, like whenever you draw.
Yeah.
But yeah, octet rule and formal charges, that's what you're always kind of analyzing.
Also, I was looking at this one, I-4, and on the key it said it was sawhorse,
Yeah.
but on the paper it
Oh,
said
seesaw
seesaw.
is the same.
Oh, it is the same?
Yeah.
Okay.
Yeah, either way, seesaw, sawhorse is
Okay.
a little teeter totter.
Okay. I just want to make sure. And then with this one, I was curious why carbon is the central element on this one. What process you would have to go to determine that?
Usually it's kind of like the least electronegative in the center, which kind of helps, but doesn't always work. But sometimes you have to play with those too.
Just to see what makes sense.
Yeah, because it's either going to be nitrogen or carbon.
Right.
Would be the only thing.
Yeah. I mean, I was going to put nitrogen in the middle, but after doing a little bit more research, found that carbon was supposed to go in the middle and not nitrogen. But I was just curious if you had any like tricks or anything like that. And then I was also curious how to tell if something is polar or non-polar.
So if it's polar, there's usually some unevenness, and then non-polar means like it's fully symmetric. So like water, so you can, and it helps if you look in like its parent geometry family. So if its parent geometry is tetrahedral, well, it breaks the tetrahedral symmetry, right? Because it only has 2 atoms and then 2 lone pairs, so there's already a break in the fourfold. So that kind of helps you see that it's polar.
Yeah.
Or just like recognizing that it has like lone pairs on one side.
Okay. Because I was.
Yeah, so same thing like ammonia, right? So that's uneven. But then methane has 4 hydrogens in each direction, so that's.
It would be polar?
That would be non-polar.
Non-polar.
Yeah, so that one is fully symmetric with the tetrahedral 4-fold symmetry, so that would be non-polar. Same with this one, that would be non-polar, right? Again, then it's all cancels out.
Okay, so non-polar is if it's symmetric, I guess.
Yeah, fully symmetric.
Geometrically polar, right? I mean,
Symmetrical.
symmetrical. That's
Yeah.
right. Okay.
And then you could also think about vector adding too, if that works.
Okay. Cool. Thank you.
Yeah.
Will we get our finals from last term?
I wasn't planning on it, but if you want them there.
I would like mine.
Okay, I will. Do you have lab today or?
No, Thursday.
Okay. Yeah, I'll have it for you Thursday then. That'll give me time to hunt for it. Did I not staple the?
None of it's stable.
That just makes me want to shoot myself as everything else wants.
No, that's the post lab. There's another one, so.
I am so sorry. I didn't catch that. I would not have done that. Oh man.
So is that all just the lab? Is there any like take home homework?
There's homework and lab, but they're in 2 piles. But I did not mean to make a disaster. Anyways, that pretty much describes this week. All right, so as everybody is probably well aware of, we all are having internet issues, which meant that I didn't put your quiz grades in, so I apologize about that. I'll try to get those in, and everyone should just be getting 10s anyways, but again, obviously none of us were able to accomplish anything. So let's see. Oh, I was going to do something, so let me do that right now. So this was a request that I share my OneNote book, so I'm going to try something differently. All right, well, I'll have to try that again because it said it was not valid for the notebook. That's irritating. All right, so we'll have lab today. And again, I apologize, I forgot to hit the staple button apparently, and then I didn't realize that they were all unstapled, so I created a disaster. Yeah, on the copy machine, and I just didn't hit it. Because I've been trying to get set up for demo and everything else today, and I didn't have internet, yada, yada, yada. All right, are we ready to get started? If I need to rerun lab copies, I can do that too, if it's now just too much of a disaster. All right, so I'll try to do the notebook sharing thing. I don't know why it told me my link is invalid, and I didn't get to do it earlier because we all didn't have internet, so I apologize. I'm behind apparently. All right, so let's go into chapter 9. So chapter 9 is pretty dense. So we want to go slow, ask questions, and of course let me know what you don't know. And so your book kind of starts off with this diagram. And really it's not the best introduction to it, but let's just kind of let's start more simply before we try to analyze what the heck they're trying to showing us with that picture. And so let's just think about hydrogen, and we want to put what happens when hydrogen bonds to make diatomic hydrogen. And so the first question is, well, what orbitals do we have? So what orbitals does hydrogen have? So S, right? So it only has our one S. And let's see, did I put a periodic table? No. But right, we should know that from our periodic table that it just has a 1s orbital. And so if we want to make our molecular orbital diagram, so now this is what we're going for. So we're trying to mix our atomic orbitals. So these are our atomic orbitals. And so then I suggest kind of labeling them and then drawing them out. And so the little lines represent our orbitals. And so we're starting with 2 orbitals, right? So when we mix them, we should have 2 molecular orbitals. So I just drew a circle. And so now we have to think about mathematically the ways they can combine. And so we have, again, this is just mathematically. So they could be called what's called in phase. And I'm just using uncolored shading. You could use both colored, but just by convention, we usually say if they're in phase, it's uncolored or unshaded. And again, they match, right? So they're in phase. So in phase. And so that means that they can come together. And so we'll draw that in a second. Or actually, let's just draw that right now. And so now we can draw our 1s sigma bonding orbital. Now this is just sigma bonding, right? Our head-to-head connection, that's all we're showing here. And we can call this our 1s. This is our bonding orbital. But of course, mathematically, we could also have the combination where they're not in phase. And so that's usually just represented by 1 unshaded and 1 shaded. And so now we say, right, they're out of phase. Sometimes you can see representations, again, just so we're clear, of negative and positive or something like that. But I prefer the shading. But again, if you look at other references, it may use this convention. And so now, so you're just looking for, are they the same, negative, negative, positive, positive, then that means they're in phase, or if they're not matching, out of phase. And I'll write that up there then, right? So then we could, again, it doesn't matter what we could call it negative, negative. The point is they're in phase so they can match and bond. And so now we have to write this out of phase combination. So this is our anti-bonding orbital. So this is not favorable, right? We don't want electrons in here. And so this is 1s sigma anti-bonding. And that little star, again, means anti-bonding. So that's kind of unfavorable. And well, now we need to fill in the electrons. So we haven't done that yet. And these lines just kind of show what orbitals are contributing to these molecular orbital diagrams. Now these are mixed MOs. So right, we could say these are our MOs, or molecular orbitals. And now we need to fill in our electrons on here. So how many electrons do we have total? So 2. And right, we might want to write those little electrons, or little half arrows, to begin with. And okay, each one had 1 in the 1s. And then just like before, right, when we were filling in our little orbitals, each one of these suborbitals can hold 2. So now we just fill them in. So now 1, 2. And now, right, that's it. And so let's go ahead and look at bond order and how to calculate that. and we'll see why it's relevant. And so now we're looking at bond order. So bond order is given by this formula. And so it's something of number of electrons in bonding minus number of electrons in non-bonding, or sorry, anti-bonding, divided by 2. And so now the next step is, how does this match with our Lewis dot structure in theory? And so for hydrogen, I probably should have made us draw out our Lewis dot structure before, but it's simple enough. We can slap it down. All right, this is what we expect. We expect a single bond. Does that hold true from our MO bond order analysis? So let's see. And so we have 2 electrons in our bonding orbital. Again, that's our sigma bonding. So sometimes we may have non-bonding orbitals. So 2 minus, so we have none in our anti-bonding. And then divided by 2. And so that also gives us a bond order of 1. And so that's good, right? That all matches. Nothing tricky is going on. So we can tell, right, just 2 1s orbitals coming together to make a bond. And of course, this is thermodynamically favorable, so it's lower in energy. And so that's also why our molecules form. And then, so this is energy on this side. And then obviously our higher energy anti-bonding orbitals, those are unfavorable. And so now this kind of brings us to this little chart here. And so now we could do this for all these species. So we could use the same basic MO diagram here. So these are all in the first row, so they just are invoking the 1s in all of them. And so we can go through some of them to see how we get this. And right, we can also compare this to experimental observations. And so apparently they have made this species called H2+. And well, let's go ahead and draw that out. So now you'll draw out a million MO diagrams. And so for our first row, just invoking 1s, it's pretty simple. And so we'll start with our same framework. So our 1s orbital from one hydrogen, then our other 1s from our other hydrogen. And then of course now we have a plus sign, so we only have 2 electrons, so I'll just put 1 there, leave that one with none. So same orbital combinations, so our in phase 1s sigma bonding, and then our next 1s sigma anti-bonding. And then we'll fill in our electrons. So again, we just had 1 now. And so this is where that bond order of a half comes into play. So now we can see that for ourselves. And I'll plug that back into our formula, right? So now we just have 1 electron in a bonding orbital minus 0. So divided by 2. So that gives us a bond order of a half. And now what is that telling us? If we go back to the chart, right, so they just have this half bond order. Well, what does that mean? And so now these 2 characteristics, right, bond length and bond energy, so this would have to be determined experimentally, maybe through crystal structure and then some sort of gas phase calculations. But now compare, right, H2 versus H2+. So what can we say about those species? What do you notice? Or just some simple observations.
From the experimental data, H2+ has a much weaker bond energy, a longer bond length than the H2.
Excellent, right? And so that's all we want to take away. So we can show that, well, this bond order of 1/2, so now we see, right, it's longer, less energy, so it's weaker, right? So it's more loosely held. And again, right, probably our bond length gives us that best indication of how loose that is. So that's kind of cool and helpful, right? So now we're getting kind of more details And, you know, if we had tried to draw a Lewis dot structure for this, right, we'd be kind of confused. So we'd probably draw, I don't know, we could try to draw something like that, right? But now we're kind of seeing the limits of Lewis dot structure. It's still powerful, right? You still want to use it, but yes, you may get to some weird scenarios where you need kind of MO theory to give us a deeper picture. And so go ahead, take a minute now, see if you can do helium-2 on your own and prove, well, why doesn't helium-2 exist? Why is helium not a diatomic? Does someone want to throw their helium-2 on the board? How are we feeling about helium-2? Emily, you want to go for it? You look excited.
Should I go on that side?
Yeah, or wherever. You can find some space.
Alright. So there's one helium.
That looks good. Excellent. My only slight criticism is you have full arrows instead of half arrows for our electrons. But other than that, it looks excellent. So did everybody get this? So right, our helium, so our 2 electrons came together. And I'll go ahead and copy it. It looks good. And so right, kind of the key, we're filling everything in. So we have our helium, 1s, 2 electrons. Helium, 2 electrons, our 1s. And so just like he did on the board for us, our in-phase combination, out of phase. And of course, right, this is unfavorable though to have these electrons in that antibonding orbital. And then of course, as made apparent by that formula, right, so if you have electrons in your bonding orbital, but then the same amount of electrons in your antibonding just cancels out. And so, right, bond order of 0, so that's where it does not exist. questions about that one? So are we feeling okay about at least
I do
one
have
S?
one question. So I'm trying to wrap my head around just the diagram itself. So the electrons in the orbital, basically the orbital anti-orbital, are those just kind of from the heliums on the sides? Like, where do they come from? Because I know helium, two heliums would have 4 electrons. So are those same just electrons on the sides, or?
Yeah, these are the same ones. So it's showing, right, the helium is each bringing 2. So I'm just writing what we start with, right? So if you have each helium, because we might do later like an N and an O, so right, nitrogen brings 5, oxygen brings 6. So that's why I have those electrons drawn there. So yeah, they're just drawn kind of twice. First we started them. So what are our atomic orbitals bringing? So each one brought 2. And then how do we redistribute them in the molecular orbitals?
Okay, gotcha. Thank you.
And so that will help you, right? So counting is always key in chemistry. So, right, you want to count how many atomic orbitals do I have? So, right, we had 2. So that means I have to have 2 molecular orbitals mixed. And then same thing with your electrons, right? I brought 1, 2, 3, 4. So I need 4 in the middle there once I go fill them all in. So just simple counting like that will go a long way. All right, before we go into the next diatomics, well, let's break this down and what they're trying to show us here. And so let's look. And so we started off. So this is just showing another pictorial representation of what we just finished drawing, right? And so this is our 1s bonding orbital. So this is, right, H2 molecular orbitals, except they went and showed all your other possibilities for our p orbitals. So let's look at that. So, right, this is the 1s. This is the anti-bonding, right, 1s out of phase combination. And then now what it's showing here, so now we've gone to the 2s. So just note that, right? So it's showing all your orbitals. So 2s, and so once we go to the second row, normally, so like, lithium, so starting with lithium, I usually start ignoring the core electrons, right? Your 1s, so you're not drawing in all these things all the time. But they're just showing it. And then, so right, with our 2s, we could have another possibility for the in-phase combination, so that's what's being shown here by this ball, right? So it's all one big ball, all in phase. So now that's our 2s sigma bonding combination. This is now the anti-bonding combination shown here. So from our 2s, so anti-bonding.
So for everyone that has like an in-phase bond, they all also have to have an okay.
Yeah.
So they're together, not or.
Yeah, so it's always, and so the thing with that though, is it may be much higher in energy, so kind of where it is, we have to kind of figure out, and that's what we're going through. But yeah, mathematically you're correct. It always has to have the in phase and the out of phase. So that's just math. And so we'll look at some mixing as we go on. But then next, so now these are our p orbitals. So now this is trying to show, and so notice them, right, they call them px. So this would be from any in-phase px combination, right? So it's showing the through space pi bond here, right? So that's what that pi is for, showing that pi, the through space interaction. We usually denote it like this. And so same thing, so now this is just the other plane. So we had px, now py, again showing in phase. And so notice they're at the same level, right? So they're drawn at the same level on the paper. And so that again means that they're degenerate, or the same energy. Degenerate. And that makes sense, right? So px, py, they're just the same, just in different axes. I'll try to draw my, again, I'm not an artist. And so again, that was our 2p. And so then this one is now our in-phase bonding. And so this would be PZ, so going this way. And so they are in phase. Oops. So sometimes we could draw them, so I could draw them normally, kind of like this. And so remember, right, p orbitals have one shaded, one unshaded side, so then the two unshaded are coming together. Sometimes you see it written like this as well, where these have like merged to create your bonding orbital there. And so this would be, right, our PZ, but it's a sigma bond. So make sure you label that. So our sigma PZ bond there. Again, just because it's head-to-head, right, so that's, the sigma is describing how that interaction is, a head-to-head interaction. And so now we need to answer, well, where did those anti-bonding orbitals go? And so notice, right, anything that is bonding is going to be lower in energy, so that's favorable. And so now here are the corresponding anti-bonding orbitals, right, to these pi bonding ones we had observed down here. So they draw them like this, and then we'll just draw them with the opposite shading. So there's our pi anti-bonding to px orbital, and this we're calling py. And if you want to note, right, these two are related, you can, or just kind of see that, appreciate that. And so same thing for our PZ, right? So we had put together the in-phase combination. Well, we need the out-of-phase combination as well. And so that is up here. And again, you can see it drawn a few different ways. So you could just draw it where the shading is opposite, or the signs are opposite. Or sometimes people do this, oops, oh my gosh. Kind of large and then small, large, to show that these kind of cancel. So something like that. And then, right, this is now our 2PZ sigma anti-bonding. So questions just about this general layout. And so you want to be comfortable kind of being able to recognize what orbitals these are, and then of course drawing them yourself. So questions, no questions? So now let's get into our demo and what I dragged out all this stuff for. And so now we're going to get into kind of diatomic molecules. And so let's set up our scenario. Well, let's first draw out two things. So go ahead and draw me the Lewis dot structure of nitrogen and oxygen. And we'll go from there. Just draw the Lewis dot structure for these two things. So if you're in the chat, you can describe your structure. I'll give people a little bit more time. All right, so describe your N2 structure. What does it look like? How many bonds do we have? Single, double, triple?
Triple bond between them and then one lone pair on each nitrogen.
That looks good. And then what about oxygen?
One double bond between the two oxygens and then two pairs of lone electrons on each side.
All right, so everybody get those structures, draw them out. And so right, pretty unassuming, so they look like they're all paired. But let's look at their behavior. So let's see if their behavior matches these diagrams. And so again, right, it all looks like the electrons are paired and happy. And so let's test that. Oops. And let me see. Sorry, give me 1 second. There we go. Fancy here. And so this is a really strong magnet. So I have this magnet here, and obviously they're held together so they don't slam into each other. And so what we expect, so if they are both indeed truly unpaired, so I have, and if you see Nicole in the stockroom today, give her a huge shout out because, you know, like you all know, the internet is down. So she was almost unable to purchase liquid nitrogen for us today, but luckily she has a relationship with them, so she was like, I'll pay you later. Because they couldn't, without internet, they couldn't take payment. So it was a mess. Give her a big thank you. But so we have liquid nitrogen in here, and so we're going to see how it behaves. And so let's actually do that. So write nitrogen, and if oxygen and nitrogen are indeed, again, both unpaired like we were just looking, it should pass through without any issue through the magnet. And so let's watch nitrogen. And if you need to move and get up closer, you know, now's the chance. And so right, just kind of runs through. Right, doesn't look cool. All right, nothing's really happening. So we could play with that later if we're unconvinced. And so now let's try to condense oxygen. So what do we have to do for that? So I have my oxygen tank set up here, and then now I need to use the nitrogen to condense it. So I'm going to try to put it in this tube. And I forgot my liquid nitrogen glove, so that's fine. All right, so I'll just let this cool for a minute. Off camera here.
So we're saying the nitrogen passed through because it's diatomic?
So right now the nitrogen just passed through because, yeah, it's diamagnetic, so meaning that it has all paired electrons, right? So if we go back to our structure. Oops. Hang on. I screwed it up. So if we go back to this, right, what we're saying is they all look like they're all paired, right? So with both of them, like there's no radical, right? There's no one electron. So it looks like they're all paired. So I guess we should write, right, we expect both N2 and oxygen to be diamagnetic, which means all paired electrons, right? So it looks like from this diagram, they're all paired, so there should be no unpaired. And so let's go back and see if that is true. So I'm just cooling this down, so now I have to open up my oxygen. So I'll open that up gently, and then hopefully we'll get nice blue liquid in here. This is the part I don't like. Oh, oh, I don't know what that was. Come on. There we go. So you see the blue coming out? So that's liquid oxygen. So now you can believe me when I say liquid oxygen is indeed blue. Okay, so that's going to be cooking for a while. So again, blue oxygen. And let's see what happens. And so notice how it clings to the magnet, right? So can y'all see that? Again, you can get up closer. We can do this again. But notice that, right? It's sticking to the magnet. It's very weird. All right, some more. Right, so notice how oxygen, right, is sticking to it. Pour out all my. And so again, right, we can do. Now that's just going to be annoying. PV equals nRT. But, all right, again, we'll do the liquid nitrogen. I'm trying to save some. But it just passes through, right? It's not catching on the magnet. And so we can repeat that if we need, right? But now we're asking, well, why did oxygen behave like that? And so the key from that experiment is, well, oxygen, it kind of stuck to the magnet. And well, if it's sticking to the magnet, then it's actually paramagnetic. And so paramagnetic means that it has to have an unpaired electron at least. Well, that's weird, right? So our Lewis dot structure doesn't say that. And so this is where our MO diagrams come into play. And so let's first start, we're actually going to start with oxygen, or kind of a generic A2 mixing diagram. So A2 diagram. So this would be appropriate for oxygen. And we'll go through all this in a second. Oh, that looks like CO2. So, right, so this is oxygen would be appropriate. And so let's just start. And so again, we care about just our valence orbitals. Does anyone need to see this done again? All right, so at the end, we can freeze marshmallows on liquid nitrogen and eat them. So that's what that's for science, I mean. So I'll be after we get through these MO diagrams. So you have something to look forward to. And so we'll start off, and so I'll add to this, there's going to be no SP mixing, but right now we don't know what that word means, but we'll go through this. And so we just want to set up, right, our generic A. In this case, I'll first write our generic template, I'll call it, and then I'll rewrite it and refill it for oxygen. And so let's just start. So if we're on our second row, again, we might be doing oxygen, nitrogen, carbon, any one of these diatomics. But again, we'll note the distinction. And so we have to have our 2s orbital. And I'm just kind of setting up right now. So 2s. And then we also will have our 2p. And so, right, our 2p that has 3 orbitals. And so notice, right, our 2p is a little bit higher in energy than the 2s. And so I'm not going to put electrons right now since I want this to be the generic diagram. But then we can think about how they'll mix. So we're kind of redrawing what we did here, but just making it a little clearer for our scenario. And so let's go through this. So just like before, we have, right, our 2s sigma bonding orbital, so in phase. Then just like before, we have, right, our out of phase, so 2s sigma anti-bonding. I should have given myself a little bit more space. Yeah, and then it's still kind of sandwiched in, though, at least right now, right between the p's. So even though it's anti-bonding, right, it's still not quite as high as a p orbital, but then we'll kind of go into that. And so next, and this is just energetically, so next is going to be the pz orbital, so our 2pz sigma bonding, which I need to draw the shading. So again, in phase. And this is lower in energy than our pi bonding, right? So this is a more direct interaction, so that's more energetically favorable, so that's lower versus, and then I'm drawing them really close together to show that they're degenerate. You could also draw them kind of next to each other. So, right, you could have also drawn them like that. That's confusing to me. Either way, and so, right, this is our pi bonding orbital. So our 2p pi bonding, so px and py. So we can draw those in. So in phase. And then now we have our out of phase, right, anti-bonding. And so that's just, that's not as high, right, because again, pi bonding not as direct, so now, right, it's not as low, but it's not as bad, right, so it's kind of a trade-off, which we'll see. So now this is our 2py and x pi anti-bonding. And then, of course, our last one is this one with our opposite shading. So that's going to be our 2pz sigma anti-bonding. So again, from that one. And so as you kind of see, right, they'll get a little bit repetitive. So if this is our template for oxygen, we can either recopy it or go ahead and fill it in. So like I mentioned, I want to rewrite mine, at least the middle part, just so we can have our blank template. And so now I'm just kind of redrawing at least the pictures. The pictures are what I like a lot. So just filling in, and I might want to put some labels. So our 2s sigma, 2s anti-bonding, 2pz sigma, 2pxy pi bonding. And actually, I'll go ahead and draw them next to each other. And then our 2pxy pi anti-bonding orbitals. And then finally, our last ones, so 2pz sigma anti-bonding. And so again, just quick sanity check. So we started with 8 atomic orbitals, right? So each one had our 3 p's plus our 2 s's. And then once I redrew it, I should still have 8. So 1, 2, 3, 4, 5, 6, 7, 8. Always good to double check your sanity. And so now this is for oxygen. So how many electrons do we have for oxygen? Now we're just looking at the valence ones. So 12. So start at the bottom, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so now, what does this MO diagram show us? And maybe does that explain now the behavior of N2 we saw? I apologize, I forgot to switch back on the other screen.
Yeah, because in the final orbital, there's, or in the there's 2 separate electrons there.
So excellent. So right now this is showing us, just like he was saying, right, since this was a degenerate orbital, it ended up being that we actually have some unpaired electrons. And so now, right, we're seeing our unpaired electrons. And so while we're looking at it, let's look at some other terms that go on with MO diagrams. And so usually they ask about the HOMO and the LUMO. So HOMO stands for highest occupied molecular orbital. And so the LUMO would be lowest unoccupied molecular orbital. And so again, those are just the orbitals people are interested in. So always the question is, right, what's our HOMO? So which one is our highest occupied? And that usually tells us something interesting. Again, in oxygen's case, now it's showing why it's paramagnetic. And you can add that to your unpaired. Again, it's paramagnetic. And that's why it had that strange behavior with our magnet and clung to the magnet, because it did indeed have unpaired electrons. And then, so this would be our LUMO then. All right, so LUMO, so lowest unoccupied. So you could go on and on in theory and keep going through, right? Well, we have, you know, a 3p orbital in theory and all those higher energy levels, but they don't really matter, right, if we're not invoking them. So we only care about usually the next highest. And usually why people care about the next highest is this is kind of open and empty for bonding. So sometimes if you were trying to figure out, well, can O2 itself be a ligand and bond with something, then you would kind of look at the LUMO or HOMO, right, and try to figure out how it might interact. So the LUMO could maybe accept electrons, and the HOMO, well, it has, you know, 2 maybe to accept, or it could try to donate those 2, again, if your MOs are aligned.
Do you ever have a situation where the electrons like jump a level and your LUMO's below your HOMO?
Nah. Yeah, because then you would just call, yeah, I don't think that would happen. It would just switch your LUMO, HOMO. So now let's look at N2. But we're going to see there's actually a little caveat with N2 as well. And so let's look at this picture to kind of help us. And you might want to star this, or like, I think your book should have a variation, although I was having issues trying to find it. But this is a good kind of cheat sheet for all these diatomic MO diagrams. And so this is just, right, the order of all your orbitals. But let's kind of look at it. And so, right, we had just finished oxygen. And so it looked just like this, right? And so go back. So you might have to check yourself for sanity, right? So we had our s orbitals, then we had our 2pzs. So we kind of had single, 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 and then 2 degenerate. But look at nitrogen. So what do you notice about nitrogen? It's really nitrogen on down has all this same pattern. But what do you notice? What you, sorry. Exactly, right? So these things switched. So we had, so this was our PZ here, right, with our sigma interaction. But now with nitrogen, and notice nitrogen on down, it's actually higher in energy. And so why that happens is because of SP mixing. And so we may want to add this to our chart here. As so once you get to nitrogen on down, you do have SP mixing. And so before we get into how they mix, well, how come oxygen, fluorine, and neon don't mix? Well, with these elements, the gap between the s orbitals and p orbitals is just a little bit more, that they do not invoke mixing. But then once we get down to nitrogen and carbon, they're a little bit closer together, so they do have mixing. And this is always a thing that chemists will talk about, is like how much mixing to invoke, and that's where you get into more computational chemistry. And it is tricky, right? If you're trying to do an MO diagram between like nitrogen and oxygen, then it's like, do you have mixing? Do you not? And that's where computational chemistry can help, but that's kind of the general rule. And so now let's repeat that. But now we're going to make our A2 for SP mixing. What's a fun color? Now we'll do A2, and this is for SP mixing. And so this would be appropriate for nitrogen. And so now let's look. And so kind of what's helpful before we get into our diagram is we want to think about, well, what orbitals can mix, and then what is that going to look like? And so let's think about our SP mixing possibilities. And so which orbitals do you think will mix, first of all? Any ideas? Might be able to guess. Yeah, but which P? Yeah, so PZ, right? So whichever one is in phase. So we have, so we can have our 2s, so I'm going to go ahead and bring both of them. And then we want to mix them with our PZ orbitals. And I think everyone was kind of seeing this, but right, that's a good first indication. And this also helps, right, figure out what orbitals can actually bond and interact. It's like, does it even make sense? Can you look at it, right, and like, oh, they kind of line up. And I'm going to post this later. I just kind of wanted to show you. So I have this book that I'll post a chapter to. And so it has like the same fun pictures, and like it kind of gets into the math a little. But again, what's really cool and what I want to emphasize is like a lot of this is really just, yeah, picture mapping and graphing, and it really does give us a good understanding of these complex math situations, right, that we otherwise just have to depend on computational chemistry. And so now let's look at how they're going to mix. And so it's kind of easiest to figure out kind of the best and worst case scenarios, and then we'll kind of figure out what's in the middle. So obviously the kind of best or most favorable, we should say, would obviously be the all in phase combination, kind of like I've drawn already. And so I'll just redraw this. So right, best is where they're all in phase. So these would be the same phase. The inner parts of the PZ are obviously the same phase as our s orbital. And so now this makes something that looks like this, right? So now our sp mixed. And the lobe is showing, right, we have all our electron density in the middle, and that's coming from our bonding, so it's going to be a sigma bonding. And so that we expect to be our lowest one. So we'll redraw this later. And so now let's think, well, okay, this is the best combination, but what's the worst combination? And so the worst combination is when the two lobes in the middle are out of phase. And well, how can that happen? So if we have, right, our s orbitals are out of phase, and then our p orbitals are out of phase, but then they're in phase with the bad combination, right? So they're matching, and so this makes the absolute worst combination. So you can kind of, again, pictorially smash them together. So now we have a really large unshaded blob here. So this kind of gets a little smaller, neutralized a little. And then, right, our large shaded blob. And so this is the worst combination. Again, electron density in the middle. They're not in phase, so that's super anti-bonding. So that'd be like way high in energy. Yeah, so that would be bad. And so, right, if we fill this up, probably in the case of like, well, neon 2 doesn't have mixing, but whatever like N2 species is with filling up electrons, that would be bad. And then, so now let's look at our kind of other scenarios. And so now we could have the scenario, well, what if the s orbitals are in phase? And the p orbitals are in phase, but they're not in phase with each other. Oops, I drew that wrong, sorry. So it looks something like this, right? So this is in phase, this is in phase, but then these are out of phase, so that kind of just cancels. And so pictorially, we can draw something, you know, like this, and then we make them small. Oops, a little bit larger. And so I would call this probably like a non-bonding orbital with our sp mixing, so it's essentially non-bonding. And then we can also have our other kind of bad, but not too bad scenario. So what if our s orbitals are out of phase, but then our p orbitals are out of phase, but out of phase with our s as well. So again, it cancels out and leaves us with this, where it's kind of bad, right? Because we have opposite phases in the middle, but it's not as bad since the electron density is on the outside as opposed to the middle where the antibonding is. So this is still formally sigma antibonding then, but just not as bad. All right, so now let's put them in order. So we'll go ahead and draw our A2 diagram again and then figure out where these all fit in. Let's see. It's a good color. Let's do green. So now we'll do our A and our A. And again, this is just our template first. And so we still have our 2P, our 2S. So I'm just kind of drawing our framework. So 2P, 2S. And so now let's start figuring out our mixed orbitals. And so we said, well, this was our best one. So this is going to be, right, our lowest in energy. So now our 2 sigma bonding, and I'm going to go ahead and draw at least somewhat of a picture so we can tell. All right, so that was our really good combination. And so if we were comparing it to kind of a mixed versus an unmixed diagram of the same one, we should have this be a little bit lower, so that should be more energetically favorable to mix in this case. And that would mean if we were to take nitrogen and make its unmixed diagram versus its mixed diagram and compare those energy levels. So this is nice and low. And so then we have to figure out, well, what about our anti-bonding, right? That has to fit in mathematically. And so next is going to be this one, right, where it's anti-bonding, but we've kind of minimized the electron density here, so it's still not too bad. So now this is next. So 2 sigma anti-bonding. Our minimized electron density. And so then this is where kind of what we'll call the flip occurs. And so that's because this is essentially now non-bonding, right? So we paid the price. So we made this more favorable. So that's low in energy. And so now we kind of made this our non-bonding. So now this is going to be not as favorable. So it's going to be more towards the middle here. So I'll put that in the middle with our sigma interaction. And so we can still call it, bonding orbital, but, again, with our electron density being minimized, it's kind of non-bonding. And then, so that means below it, that's why our pi orbitals then are below it, right? So now they're lower, since this is favorable pi interaction, so now this is our pi bond from our px and py. So that's why that was next on the energy list. So more favorable interaction. This is kind of non-bonding-ish, hanging out. And then we can fill in the rest. So right back to our pi antibonding orbitals, so px, py antibonding. And then, of course, at the very top is where we paid our price. So you would not want to put anything in this orbital. And so now that is our 2 sigma antibonding orbital, our very bad one. And so, again, double check yourself. Make sure you have 8 in the middle. So 1, 2, 3, 4, 5, 6, 7, 8. And so this is our framework. So I'll go ahead and recopy it for nitrogen so we can fill in our electrons. So this list, or and so again, we can kind of re-sketch it, recopy it, but also get yourself comfortable. Again, I'll refer back to this chart. So on an exam or something, you might want to just be able to glance at that. Oh yeah, that helps me, right? I know what orbitals those are. So you can re-sketch them, which is just the same as this, right? They're all the same information. So I'm trying to emphasize that it's all there for you. And so I'll do my quick sketch. So just laying out what we started with. And now we could fill in our electrons we wanted on the side. So each nitrogen bringing 5. Then I don't know what I'm doing there, sorry. Drawing in our orbitals. Again, just because it helps me, it's more for me. Our anti-bonding. Oh my gosh, trying to rush and I got all the shading mixed up. So 2 sigma anti-bonding. Then we said we had our p orbitals. So 1, 2, so our pi bonding. Then essentially what I call our sigma non-bonding, but still formally bonding.
Why is it like not bonding but technically bonding?
Right, they're still in phase, so if we fill in electrons, we still want to say that they're a bonding orbital for our bond counts. But then, right, I just say non-bonding because the electron density is on the outside. So, right, not a lot of electron density there for the bond, but. And then back to our pi anti-bonding. And then, of course, our very bad sigma 1. And then again, always do your sanity check. So 1, 2, 3, 4, 5, 6, 7, 8. And so now we can fill in our electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is kind of cool. So we have we can get a lot of information from this. So now we're proving why nitrogen was not exciting and just passed through our magnet. So yes, it has our paired electrons, so no unpaired. And then this is just a nice thing to note on that, okay, well we have, our kind of formally non-bonding orbital and our electron density is on the outside. So now we're kind of getting a hint at maybe how nitrogen can go on and bond to if our electron density is on the outside. And if we go back to our structure, it's kind of showing, well, maybe this is where our electrons are hanging out in this orbital. So it's kind of giving us an idea that, yeah, this is why we have lone pairs drawn in our Lewis dot structure. So that's kind of fun. All right. And then, we might as well do our bond order then.
You said that sigma non-bonding orbital represents the lone pairs in the Lewis dot structure.
Yeah, and that's just probably, so we're basing it off of, right, we have our Lewis dot structure, but then we're looking at this and notice, right, well, the electron density is going to be on the outside, so this is probably representing that then, where our electron density is there.
But how would it represent both lone pairs when there's only 2 electrons in that orbit, like in that small structure?
So the thing is, it's not going to match, right, perfectly, because you're just trying to get a sense, too, of, like, what orbitals there are. And so that's kind of like the limitation, right, with our Lewis dot structure versus our MO diagram. And so our MO diagram is giving us just like a more detailed understanding of like where they're occupied really. And so that's kind of what that's showing, right? So we have 2 electrons occupied in this formally sigma bonding. And so we do have this kind of like 2 pi anti-bonding. And so maybe that's also where some of those electrons are. Because, right, you don't really just have 2 electrons necessarily hanging out there all the time. They're going to be flowing around, moving, and you're just trying to get a sense of, well, where are they?
Where are the possibilities?
Yeah.
And since those are out to the side dimension, maybe that's where they are.
Yeah, exactly. So it's kind of it, but then it's also telling us too, because they're here, but this could be primed to bond then, right? So we mentioned, so this would be our HOMO, and so this would be good for bonding. So if you were trying to figure out, well, how can nitrogen act as a ligand, you might be looking at this orbital and kind of, again, what's in phase with it. So now if this is occupied, again, maybe that nitrogen can come on and attach to a metal like we've seen, and then you try to invoke, right, this orbital. Because that's kind of where this goes on and on too. So we're just doing the basics now, but then if you were to do like, more inorganic chemistry, then you're like, well, let me take this bond and see what is it in phase with my metal orbitals, right? So then you'd probably need a d orbital to be in phase. So that's kind of where this is going. It's like if you have a d orbital, so this is dz squared, maybe it could align. Yeah, and exactly, right? You just use the pictures. It's like, does it match up? Could it maybe align? And then, obviously, you go into more the MOs and see, do the electrons match and all that. But that's roughly where we're going. Questions so far? I'm just trying to gauge how we're feeling on this. Let's do another practice. So let's see, because I think the rest of this chapter is a lot of hybridization, but I feel like we covered that last time, or last chapter. So now let's try some other. So see if you can come up with the MO diagram for C2, and then we'll compare that to C2 minus and C2 plus. So I'll give you a few minutes to at least kind of get started. So maybe start with just C2, and then we'll check in and see how everybody's doing. So does someone want to put C2 somewhere on the board for us? We could do that bar board too.
I can do it. Is it just the MO?
Yeah, if you just want to put the MO diagram for C2. Yeah, you could also do on the other board, like that board if it's more space on there.
Okay, so now we just first set up the diagram. First you have the lowest energy level, the big SP sigma bond at the bottom, where the two electron densities are touching in the middle. And then next we have the sigma antibond that's smaller, the small electron in the middle. And then there's the pi bond that's in phase, I guess it's the laser bond. And then after that you have the sigma bond that's in phase, but the electron density is on the outside. And I think that's all we need for this one. Does it fill up electrons, which it's carbon, so you have 8 in total, 4 from each carbon. You get that. I guess you did the top one. And then so that means that since this is anti-bonding, non-bonding, and this is, these are both bonding, then you have a bond order of 4, I believe.
Okay, 4?
Because is it bonding minus anti-bonding, or is it non-bonding, or is it 2, or is it the other way around?
Yeah. Sorry, I'm still catching up to you. So 1, 2, 3, 4, 5, 6, 7, 8. And then you have, because you have 1, 2, 6 in bonding, right?
Yeah.
So
I
6.
forgot the equation works. Is it?
Oh, it's 6 minus, so bonding minus anti-bonding divided by 2.
Mm-hmm.
So,
Oh, divided by 2. I forgot about the divided by 2 part. Okay.
yeah, so
Yep.
6 minus 2, so 4. Oh, yeah, now we're on the same page. So, yep, our bond order of 2. So then we could try to draw C2. Again, kind of an imperfect structure and kind of odd. But that looks good for our diagram and our bond order. And so my other criticism, you still want to draw in the orbital even though it's empty and we don't need it, the 2 sigma antibonding. Yeah, you just want to draw the line for it at least.
Okay.
Just so we know, right, it's there, it exists mathematically, but it's not occupied.
Okay.
So that looks good. And so then if we want to change it for C2 plus, so what do we have to do, or what does that change really?
You just take away an electron.
So take away an electron, so that's going to affect, right, our bond order. And so you could, this is, right, another trick, you could also try to squeeze in your electrons on there. So if I want to do C2 plus, I'll switch it to pink. And if anyone's colorblind, definitely let me know. I just changed colors. So 1, 2, 3, 4, 5, 6, 7. And so right now we only have 7, so that's going to change our bond order. So C2 plus would have 5 minus 2, right? So what do we get for our bond order? So 3 halves or 1 1/2. So you can see, right, a little bit weaker than our C2 scenario. And so what about C2 -1? What does that change? And so again, right, we could see this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And so it also has a different HOMO. So now our HOMO is in our non-bonding. Formally bonding though, so now this kind of changes it. So we could do 7 minus 2 divided by 2. Probably give a 5/2 or 2.5 bond order. That's kind of the theme of this chapter. So it kind of gets a little repetitive, or it should feel repetitive, right? You're kind of doing the same framework.
So does the higher bond order represent how strong they're attracting, how strong the bond is between the two carbons? Like the higher, the stronger the bond?
Yeah, so roughly. And so back to like this data point, where were we? Basically, right, if you have a higher bond order, you should have a shorter bond. And so that should, yep, so all of that should kind of track in general with that. Excellent. So we might as well, let's go ahead and let's do another practice. So now let's switch over to neon. So see if you can, well, let's try to make it for diatomic neon. So go ahead and try to make your MO diagram for diatomic neon. And don't forget, right, do you need a SP mixing? Do you not need a SP mixing? So see if you can answer that for yourself before I reveal it. And then what does that diagram look like? And then we'll answer why neon 2 doesn't exist. How's our neon diagram going? Does someone, or diatomic neon, does someone want to put on the board for us? No one wants to throw it up on there? This side's been a little quiet. You do have more people over there. So walk me through it then. So first of all, neon. Do we do SP mixing? No mixing? So I see a head shake for no, right? So no SP mixing. And so remind yourself, draw a big flag, whatever. So as long as it's oxygen, fluorine, neon, right? No SP mixing. And so again, you can either refer yourself back to what I will now call our other cheat sheet, right? So this is our cheat sheet diagram to remind ourselves what order it goes in. And so let's go ahead and do that. And always good to practice without looking. So no SP mixing. 2P, 2S, 2P, 2S. And so now we can just start filling it in from our regular order, right? Our no mixing. So I'll just draw out the layout first. And we had our pi orbitals. Oh, sorry. I skipped. Sorry, PZ. Head-to-head interaction. Then our degenerate pi bonding orbitals. Then pi antibonding. Then our sigma antibonding. And again, just double check. 1, 2, 3, 4, 5, 6, 7, 8. So there's our not mixed diagram. And so how many electrons do I need for this? So yeah, so in here, so right, we have 2p plus 2s, so how many electrons? Yeah, so 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And well, this is kind of our hint right here that this is probably a bad sign. And then did we go ahead and calculate our bond order? 0. So we have 1, 2, 3, 4. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8. And bonding minus, sorry, I just didn't draw this. 1, 2, 3, 4, 5, 6, 7, 8. And anti-bonding. And so that is why neon diatomic does not exist. And so we could keep doing this. I wanted to bring up some things in case you guys get really bored and want to explore. And so the fun thing about kind of your WebMO axis, if you remember WebMO, is so right, you can feel free to go in there at any time. Actually, I was playing around with it. Oh, crap. Oh my gosh, sorry. Now I'm just clicking too much. So let's look at, so I had ran, so just like we did in lab, I started off with a geometry optimization. And then what you can do, again, just like we did in lab, we can do a job using it. And I just picked Gaussian, that's kind of just my habit. And then under calculation, they have molecular orbitals. And so that could be fun, at least just to kind of explore. But then I also want to show you like the caveat and how it's kind of tricky to compare the orbitals. They might also be in slightly different order. And that could be, you know, from the basis set, why it's not coming like we expect. But I want to give you a sense of what you're looking at, because it is kind of confusing. So then you scroll down, and then if you just hit the little, like, I don't know if it's a magnifying glass, probably magnifying glass. And so then it pops this thing up. But Gaussian is a little confusing. And so first of all, right, it's spitting in all the orbitals. And so usually your two bottom ones tend to be your core electrons here. So, right, if this is N2, this is going to be your 1s in phase combination and then out of phase combination. But notice, so even though, right, they're in phase as the 1s, the way they are drawn on Gaussian here on this computational software is it's showing that it's centered on the atom, right? So they're not really interacting. So even though they're 1s, they're in phase, we don't look at them, right, when we make our MO diagram. And this is kind of showing, yes, they're so far down there that, you know, even though they're in phase, this is going to be centered all on the atom. So those are those orbitals. And then 3 is where we start kind of with our MO diagram. So now we would say this is probably, right, our 2s sigma interaction in phase. And so notice, so they simplify it, right? So we draw like 2 balls in phase, but really it's drawing the combined orbital and giving us an electron density picture. So of course, if it's in phase, it's going to make one nice sphere that's all the same color. So you can see that. And then so if we go up one level, so that makes sense, right? The anti-bonding one, kind of like we expect. And then this is where things go a little out of order from kind of what we had done. So if that was N2, actually we'll just look at this N2, right? So we were looking, so it should be that our degenerate p orbitals are lower than this non-bonding. But if we look at this, so it has, for some reason, so the degenerate orbitals ideally should be the same energy. Again, you might see a little funky things when you run this yourself. And they're all pretty close in energy though too, right? So notice that for some reason, Gauss, this computational software, put our degenerate pi orbitals, so you can see, right, those are degenerate, there are pi orbitals, but they put them slightly higher than this, what I called non-bonding one. Again, I'm not entirely sure why, but I'm just kind of telling you, you might see this. And so to dive into it, that's where you start getting into all like the basis set and what you're using, so which one is more accurate. So that's where there could be discrepancies, but this is still a fun tool, you know, to at least say, hey, I can see at least they're relatively close in energy. And so according to this, right, this would be then our HOMO. So they keep increasing in energy. And then we can see our unoccupied one is at pi anti-bonding, which does match at least with what we expect. So then our empty pi anti-bonding. And if you go back, right, it tells you how many electrons are in there. And then, right, 0 starts our unoccupied. And then you can see the 2 degenerate unoccupied ones. And then this is more PZ mixed. So you can tell that's probably an anti-bonding. And then more bad combinations. And so it does kind of go on and on and on too with the theoretical orbitals, but so just be aware of that, right? It's going to show you a lot of stuff, but you can still kind of extract what you want to find out from it. All right, how are we feeling about MO diagrams? Feeling pretty good, maybe. All right, so this is probably a good place to stop talking because I do want to freeze some marshmallows for you guys. I mean, scientific experiments of marshmallows. And so what we'll do, if you want some marshmallows, just come up. So I will kind of freeze them, and they get kind of like hard and funny. And if you're really cool, some people can do like dragon breath.
If Camila does it, then I think
All right, I have my first break.
I'm gonna definitely do something.
Who else wants some?
Try some.
Yeah.
That was kind of crazy. My dad.
Kind of,
Oh,
I
okay.
kind of get the idea of the textbook.
When I walked in a little late, and they were like, you just finished explaining that diagram that I walked in, I was like,
Exactly.
This is during the areas,
Yeah.
and there's not really a way to get it. So, it's kind of like makes you have to go out the whole day.
Is it crunchy?
Yeah.
yeah, it's like 6 minutes.
Yeah, it makes a weird sound. Very cold. And you really just bite it.
Yeah, or like how.
It's like,
Oh. Oh.
Is your eye okay?
I said something slightly concerning.
What happened?
Actually, 4.
Just in case.
Yeah. No, I sympathize with retina issues because I have like lateral degeneration, so I have like thin retinas or something, so I always have to like go in and get scanned or whatever. It hasn't, like the only thing that was as a kid, they were like, oh, don't play contact sports.
Oh, okay, interesting. Yeah, I'll have to find out what they say.
Yeah. But yeah, I'll see you Thursday.
I mean,
Okay, sweet.
kind of curious about.
I do work at 3, so I don't know, like, I have like
can I come for seconds?
1:30 to 2:30,
Oh, yeah.
but hopefully, yeah. Thank you.
No, I'm not photogenic. All right, I will stop this stream.